Before we continue, we have a new mathematical operator to talk about, and that is the gradient. So you're going to walk away from this discussion with a new tool to put in your vector calculus toolkit. Let's start by looking at what goes in and out. So what goes into a gradient is a scalar field, and what comes out is a vector field. So this is f of x, y, z, and what comes out will be a vector field, so capital F of x, y, z. And remember that what goes into, this is a scalar field, so what goes in are locations, and what comes out are scalars. And once you run it through a gradient, you get a vector field. So what goes in are locations, and what comes out are vectors. This is in contrast with the divergence. So this is not the same as the divergence. Remember what a divergence does? A divergence, if you're taking a divergence, what goes in is a vector field, and then what comes out is a scalar field, right? So let's first of all talk about what this gradient does. It does basically what it sounds like. So if you have a scalar field, I think that altitude makes a lot of intuitive sense here. Is if you have a scalar field where, if I give you a location, it gives me an altitude. Then a vector field will calculate the slope for each of these locations. So let's start out with an intuitive understanding. If I gave a scalar field would look a little bit like a topographical map. So if this is my map and I have a mountain, I'll have like 1,000 meters over here, 800 over here, 600 meters over here from sea level. So this is kind of the mountain that I have here, and this is the peak. Everybody's very happy when they're here, and what you end up, this is going to be my scalar field. This is my f of x, y, z, meaning I give you a location here, and it gives me an altitude in return. If I were to take the gradient of that, what the gradient would give me is it would take the localized difference between 2 points and tell me all the vectors that tell me how the gradient, in not so many words, it will tell me the gradient at every point. And in the case of this analogy, it will always point uphill. So for this elevation topographical map, if I were to take the gradient of this scalar field, this function that gives me an altitude for every coordinate two-dimensional coordinate that I put into it, it will give me a bunch of vectors, and the vectors will demonstrate the amount of uphillness that exists at every point. Now that we have an intuitive understanding of how to calculate the gradient, let's look at the notation and the formulas behind it. A gradient will look a little bit like this. So the two hints that you have that you're doing a gradient instead of a divergence, let's not forget what a divergence is. A divergence notation looks like this, right? So what are the two telltale signs that you need to be looking at doing a gradient? The first is there's no dot, right? And the second thing is that you're applying it to a scalar field and not a vector field. So the gradient of f in Cartesian coordinates is going to be a little bit more intuitive. Remember, this operator in Cartesian coordinates makes sense if you view it as d by dx, x hat, d by dy, y hat, d by dz, z hat. So if you just apply that to a vector field, you get d by dx, f in the x hat direction, d by dy, f in the y direction. Just can't quite get this right. And d by dz f in the z direction. If you're in the other coordinate systems, I'll just write them out here. If you want to see the nitty-gritty of where they came from, I would refer you to Appendix A of the textbook, but I think at this stage it's sufficient to just have an intuitive understanding, conceptual grasp of what's going on when you take a gradient, and then know how to do it. The rest of the intuition, I think, will come with some experience. dz of z hat. And in the spherical coordinates, it would be d by dr f in the r hat direction plus 1 over r d by d theta f in the theta hat direction plus 1 over r sine theta d by d phi f in the phi direction. So note that what comes out are vectors, and what goes in is a scalar field. And conceptually, again, it just kind of tells you the amount of uphillness at any given point, or the gradient, as you might say. So using this operator, we're going to apply it to the potential function v that we were talking about earlier.